So my son is making fun of me as we make this video because apparently I start everyone out the same. So I can't say "Hey guys" anymore like he is making fun of me right now. So um okay, so we're going to tie into kind of a new concept you guys learned this year, water potential, or you will learn depending on when you're looking at this video, and kind of dealing with passive and active transport. And when you kind of break down what potential is water potential is the ability from water to move from one area to the next. And so obviously we know that by the process of passive diffusion and osmosis that it's going to work from areas of high concentration of water to low concentrations of water, but there's other factors that come into play. So in a general rule of thumb, when we're talking water transport, water potential, the same concept applies in that you have water is going to move from an area of high water potential to an area of low water potential. And hopefully that'll make sense once kind of, again, we're done with this. So the question I think we want to answer right away is that if you have this tube sitting right here, and I have one half of it is filled with pure water, the other half is filled up with a solution that you have basically salt, sugar, whatever it is, and water itself. And this little barrier here that will not allow that semi-permeable, will not allow that sugar, that salt, to get through. So the only thing that can move back and forth is going to be water. And so the question to you is that will the water just remain constant? Will it just remain equal like we see in the picture right now? And the answer to that question is going to be no. And so the reason is that when you start looking at the different factors that affect water potential, the movement of water, there's two things that come into play. There's the solutes that come into play, and there's also pressure that can come into play, and that can move water from one area to the next. And that's how, when we go through, we take a look at the water potential equation, Poseidon, the symbol. This would be for water potential there. Let me try to get to a big screen here real quick. Okay, equals solute potential plus pressure potential. Okay, so we've got pressure that can impact water potential. We've got the amount of solutes that can impact the water potential. And we'll kind of break these down as we go through and kind of filling out this equation. So again, the question is, okay, we go back to this guy right here. Eventually what we're going to do is we're going to relate this to the cells and hyperanisoc and hypotonic environment as far as, why water is moving from one place to the next and what could be causing that. So we take a look at first and foremost, pressure potential. Pressure basically is, if it's an open container, such as what we see right here, pressure is always going to be zero. Now, could we add pressure or could we take pressure away to one of these sides? Sure, yeah. If I would take an air pump and I would blow water into this side right here, well, we're increasing the pressure on this side. We're increasing the pressure potential, which if you kind of could visualize this, what's going to happen is that it's going to eventually push water over here. Same situation, I could I could create a vacuum over here or attach a vacuum to this, and then eventually what's going to happen is it's going to pull that water up to it. So again, when you kind of start looking at if we increase pressure potential, right, what that's going to do is that's going to increase the water potential, right? Which again, we've already said that basically water is going to move from areas of high to low. So if I increase pressure potential on this side, it's going to force water to that lower water potential side over here, okay? Same thing, if I take it away, such as a vacuum over here, well, what's going to happen? The water is going to move from the right to the left because, again, I've created a lower water potential over here compared to over here. Now, for the most part, I think what's going to happen with the pressure potential is they're going to give you some form of open container. If it is an open container and they don't give you anything dealing with pressure, just simply consider it to be zero. Now, the other thing that does come into play with pressure potential is plants. And plants, remember, have that cell wall. And most of the time, it's not going to come into play with the questions that you guys are going to get. But if you, again, push enough water into a plant cell, well, the cell wall is actually going to push back on it again. And so it will actually increase the pressure potential within that cell. But again, we really wouldn't worry about that so much. But it does come into play with probably some of your more, I guess, tougher questions that you guys maybe will see throughout the class. But so when we go to solute potential, now solute potential works a little bit differently because, again, we got to think about it as its impact on the water potential. So anytime that we increase the solute potential, okay, what it's actually doing is it's going to decrease water potential. And so which is why when we take a look at adding these solutes over here, notice what happens. The solute potential is at a negative 0.4. And the negative 0.4 is because it's having a negative impact on the water potential, right? And so it'd be no different that if you put a cell into a hypertonic environment, well, that environment has more salt, right? And so that salt is actually going to create a negative water potential because, well, there's more salt, there's less water, right? And naturally, which way is water going to be gravitated to? It's going to gravitate towards that concentration with the higher salinity, right? And so that's kind of what we're looking at here. Now, in the pure water, there's no solids whatsoever. So notice what the solid potential is again. Solid potential is 0. And so therefore, what's occurring is that we now have a higher water potential over here because it's an open container, pressure is 0, right? Solids over here, there's 0 of them. Over here, and this number is going to be given to you. It's a negative 0.4. You're never going to have to try to calculate what solid potential is. Well, and I guess I should take that back because there is an equation that we'll look at down here that you guys should not have to worry about for the AP exam, but the class we did worry about it, to where, again, most of the time that number is going to be given to you. So we've created actually 2 different environments. We've got one over here, pure water, open container. We've got one over here, open container, but it's got a solution. So there's actually negative solute potential. And so again, when you notice what happens to the overall water potential, well, here is a negative 0.4, here's a 0. And so which one has a higher side? This one over here has a higher side, right? And so therefore this one has a lower side. As we said before, water is going to work from areas of high to low. So therefore water is naturally going to be drawn to the right. And eventually it's going to start making its way over to this side of the container due to the solution. Okay. Now, as I said before, in solid potential, there is a way that you guys can go through and you can calculate this, negative I CRT. I'll explain more of this in class if you guys are looking at this back in, like the September timeframe, October timeframe. For those of you reviewing for the AP exam again, I do not foresee any of these questions coming up where you need to go through and calculate the actual solid potential. Negative I CRT. C is a concentration they'll give to you. Remember, R is a constant. Temperature is in Kelvin, so you take your 273 plus the degrees Celsius. And the ionization constant, remember, if they're giving you something like sucrose, for example, right, it's going to be like 1. If they give you something like fructose, for example, it's going to be 1. If they give you something like NaCl, well, it can divide into the sodium and divide into chlorine, so then the ionization constant would be 2, okay, if that ever does come up on the AP exam. But again, we'll kind of break this down for you guys just starting out the AP Bio class and figuring that out. So now if we take a look at this little slide over this little scenario. So we've got a hypertonic environment, right? So remember in a hypertonic environment, hypotonic. In a hypotonic environment, remember what's happening is that water is going to enter these cells, right? And so as it's entering these cells, we're looking at basically difference in water potential. And so therefore, what we're looking at is in a hypotonic environment, we have, right, a higher water potential on the outside of these cells compared to the inside, and water is going in. So what could possibly be causing that difference in water potential? Well, for the most part, we're looking at this inside the cell, all right, probably has a higher concentration of solutes. And so therefore, maybe it's got a little bit more salt, maybe it's got a little bit more sugar. Or we could also take a look at it as the outside environment has more of a pure water environment, okay, which is what we've discussed in the past with most organisms in a hypotonic environment. It's pure water. They're going to take on that water, and eventually the cells are going to expand. Animal cells could possibly explode. Plant cells, they got the cell wall to help out. They want to be there. They want to be in that turgid environment, okay? Isotonic environment, if we were going to look at the outside versus the internal environment, what would you say, right? They would both be equal, right? So whether it's at a 0, a minus 0.2, whatever the case is, we're finding where each of these cells are in an equal concentration to their environment. So therefore, water is always going in and out, just never changing concentrations. Now, if we're going to look at hypertonic, remember what happens? Water leaves these cells, right? Okay, none of these cells want to be in that situation. So why is water leaving? Because there's a higher water potential on the inside compared to the outside. And so now what happens is you probably put those cells into something that has a higher salinity or a higher concentration of solutes. And so therefore what it's doing is it's decreasing the water potential on the outside. So therefore you've got higher water potential on the inside versus a lower water potential on the outside. And that's the way that water is moving. Again, I can't foresee a lot of questions on the AP exam dealing with this in 2020. just based on the whole situations of the FRQs. But if it does come up, again, hopefully you guys are prepared.